Excellent. Okay, sorry. Yeah, so my name's Simon Sheridan. I'm based at the Open University down in Milton Keynes. I'm quite fortunate. I've been down there for quite a while, actually. In fact, all my working career. I did a PhD in planetary sciences, and I got involved with building the instrument Philae, which is currently on the lander on the surface of the comet. So, and I've been there for about 20 years now, and I'm very, very lucky because I've been involved with the Rosetta mission and also the Beagle 2 mission. So I think I'm very lucky, and I think it's mainly down to luck more than anything else, to be honest. I was in the right place at the right time to do the PhD. So I was a little bit concerned when I was asked by Jonathan to come here today, because my first reaction was, well, there's no Python at all on the lander. We use weird code, we use C. And he assured me that it's not about programming, it's basically about science talk and about what we actually did to get there. So what I'm going to talk about, it's a talk, rather than going heavy in science and astrophysics and planetary sciences, I'm going to sort of be a little bit more behind the scenes of my involvement and how we actually got to get this probe onto the comet. So as I say, so I'm based at the Open University, and I initially started as Colin Pillinger's PhD, or one of Colin Pillinger's PhD students. Unfortunately, as a lot of you may have known, he's died a couple of years ago now, so he's not around anymore. But at the Open University, the group grew, and initially we started off as a sample analysis lab, so we were working on meteorites and returned lunar samples. But then we branched out into spaceflight instrumentation, primarily the Rosetta mission. So what the aim was, we tried to build and miniaturize some of the kit we have in the labs. And then since then, we've now doing more work into optical detectors, and we're currently working on a proposal for a European mission back to the moon. So we're going to land a lander, a fully autonomous lander at the South Pole of the moon, and actually look to try to do an inventory of the amount of organics and volatiles that are there as a precursor for future manned missions. So the astronauts can actually live off the land rather than taking all the material with them. So our group at the OU, we're really interested in solar system formation, and we're really quite lucky because a lot of the material that gives us clues and understanding of what actually happened in the early days of the solar system formation actually literally fall on our laps. They fall to Earth in the form of meteorites. So through the years, we've got a really good catalogue of different material from different times. But in this inventory of material, one thing we're lacking is cometary material, because the nature of comets, they're quite fragile, they're very cold, full of volatiles, and they don't really survive entry into the atmosphere very well. They literally detonate, and you get air bursts. There have been some attempts to capture cometary material at high altitude using like the U-2 spy planes, and some material has been brought back, but there isn't a great deal of material. So obviously, with the advent of this one come out very well actually. This is, okay. What this slide here is supposed to try and show is, with the advent of the space age, there's been a number of missions to comets prior to Rosetta. But a lot of these missions are at best flybys. If there's any Americans in the room now, they'll probably be sort of telling you, oh, we've landed on a comet as well. But there's the Temple 1 mission in 2005. They actually fired literally a cannonball into a comet. So in my book, that's not really a controlled landing. But the interesting thing is, all these missions, literally, they come in at very high velocity and they're out again. So it's very, very, very in and out. So we've got some stunning pictures, and we've collected some dust, and we've got some mass spectrometer results of what's actually coming off these comets, but we don't really know a great deal about them. So this is where the Rosetta mission came in. When the idea of Rosetta, it actually, prior to the current mission that's actually in operation at the moment, there was a precursor to it. That was in the days, in the mid to late 80s. And it was an international mission with the Americans were on board, NASA were on board as well. And back then it was going to be a sample return mission. So the idea was to go out to the comet, rendezvous with it, orbit it, put a lander down, bring the sample back to Earth so that we could actually analyze it in the labs that we've got, like in Milton Keynes at the Open University. So that's what we originally really wanted to do. Unfortunately, NASA pulled out, as NASA have a habit of doing with European missions. So there was no way that ESA could fund this whole ambitious sample return mission. So they, rather than scrapping the mission, they said, okay, what we'll do is we'll delete and remove the sample return element of the mission. So we'll focus primarily on an in situ mission. So this is where the current Rosetta mission was born. So here it was, I mean, it's still an amazing, audacious plan to actually rendezvous with this comet, stay with it for a whole year, map the comet, and then put the lander down. And then it gets even more exciting because the current plan, which I'll talk about in a moment, but the current plan is actually, at the end of mission, is to actually land the orbiter on the comet as well. So it'll be a double lander mission. So there's some really more exciting things to come. So this slide is a rehash of the previous, but one with, and you can see now, the blue line on here. So as you can see, all these other missions are straight in, straight out. The blue line indicates what Rosetta's done to date. So it's actually, it's spent over 400 days at the comet now. And the plan is it will be there for much longer.
The vertical axis is the distance the lander is from the comet.
That's correct. That's the distance the spacecraft is from the comet, yeah. So
you're spending a long time close to the comet and getting close to the
yeah, and actually, down here, we put the lander down. So that's where the lander is. And at the moment, the orbiter's had to back right off, so we're currently about 400 kilometres away, and we're going to be going out even further, probably 1,500 kilometres, to actually look for the bow shock of a comet. So, okay, so in the OU, we have these huge bits of kit, and these, I mean, to say they're the size of a car, they're big. There's probably 3 or 4 tons of kit in there, and these are mass spectrometers, and they're big, heavy, nasty, noisy bits of kit. And you can see one of my colleagues there working on this instrument called Finesse, which analyzes returned lunar samples and also meteorite samples. So the plan was, when Colin realized that the mission wasn't going to be a sample return, was how can we still get a piece of this action? So he came up with this plan, which Colin often did, was, yes, we'll miniaturize that down into the size of a shoebox, and then we'll take it to the comet. And then he relied on his team to make that happen. So we did. So this is the flight model of the Ptolemy instrument. So the previous instrument, I'm not saying all the functionality, because obviously you have to sacrifice something when you go smaller, but primarily the functionality is shrunk down into this object. It's about 4.5 kilograms. On the far side, you see the silver hemispheres. They're gas tanks which contain really high pressure gas at helium at 70 bar. The bit I've got my hands all over in the little black box is the electronic side. So there's a computer in there. There's avionics and a spacecraft interface. And the rest of the shinies is there's a mass spec in there, there's some valves, there's some reactors and some chemistry. And that was me back in, 2001. And if you can just see through the hair, I don't know, but it's dark in there. I had dark hair. This is a later thing. So in the heart of the instrument is the mass spectrometer. And this is one of the things where we were able to actually miniaturize and really, really shrink down what's currently in the state-of-the-art machines in the laboratory. So what we did is we designed this small, it's called an ion trap. It's essentially, the mass specs you may be familiar with often use magnetic fields to separate the ions out. This uses radio frequency fields. So what this means is you can put an RF field on the center of this device, and ions just get trapped. So you're trapping them, and then you can manipulate them out into increasing mass range to do the science that you're interested in doing. So the thing to take away from this is basically what we've done is we've gone about it a different way, and we've kept the science that we needed, but with the improvement in the electronics and controllers, we were able to achieve this because we have to manipulate RF fields on here, which 30 years ago we couldn't do. Now it's very easy because of the technology we're carrying around in our pockets. So the whole instrument is less than 500 grams. It's less than a watt. And even back in the sort of 10 years ago, we were at cutting edge. We were working on nanotechnology. So we developed these with our colleagues at the Rutherford Appleton Laboratory, these nanotip field emitters that you see at the bottom. So what these are, they're very, very sharp spikes of silicon. And if you put a low voltage across them, you get electrons streaming out of them. So we use that as an ionization source for the mass spec. So, Ptolemy. So Ptolemy is this mass spectrometer, and the aim of Ptolemy is what we're trying to do is we know there's organic material on comets from these flyby missions, and all the models say there should be organic material there. So really what we're trying to do is we want to go there and actually categorize and get a catalogue of all the organic material, the inventory, on the surface and subsurface. And one of the other things we do is we look at the isotopes of the gases that we're looking at, and that can give us an understanding on the processes and that were going on when the comet formed and where the comet was in the solar system. So again, that fits into the whole solar system formation models. And importantly, I mean, I think this is fascinating, but more importantly is we can actually go and look at the signature of the water and see whether the water on the comet is similar to the water that we're seeing on Earth. Because one of the theories is that the organics and the water came from cometary bombardment. So that's the aims of Ptolemy. Okay, so hypothetically, we're on the comet, everything's good. We've got to actually get this material into the instrument. And the object you see on the right-hand side there, it's a drill device. And I don't know if you can actually pick out on the image, but on the bottom there's a black plate with a spiral sticking out the bottom. That spiral is like an auger drill. So the idea there is that was to drill about 30 to 40 centimeters into the comet, and then take a solid core of this ice material and bring it back into the lander, which would then be distributed between our instrument and a number of the other instruments for analysis. And there's a common carousel about that sort of size with 36 little miniature ovens on, and there was two flavors of these ovens. One was what we call high temperature, because we heat them to high temperature, and then we have medium ovens, which are a little bit lower temperature, about 200 degrees. And the reason for the differential is, on those 16 medium temperature ovens, there's a small quartz window in the bottom of them. And so what we can actually do is, prior to doing any analysis, we can actually image them with a microscope and a camera to actually get a contextual information about the sample that we're going to analyze next. Because the problem with the high temperature oven is it's a bit of a leap of faith, actually, because the drill drills, and then they tell us, yes, you've got sample in the oven. And if we analyze it and don't see anything, we start asking ourselves, is there really anything in there? Have they dropped the sample, or is our instrument duff? So So the beauty with the medium temperatures, we can actually see this sample, so we actually know what we're going to analyze. In addition, there's another, we call it a CASE oven, and in space science we love our acronyms. So this CASE, it's a cometary atmospheric sampling experiment oven. I mean, so and what's in there? Again, it's a small oven. You can see it on a 2p piece, just about in the top image. And it's packed with highly adsorbent material, and it's very similar to the material that you get in the little sachets in your trainers when you buy them that says "Do not eat" on them. And this is highly adsorbent material, and the idea is we can actually put that oven on the carousel when the comet's down, and literally just integrate over a long period of time all the material. It just sticks down, and then we can then bring it into the instrument to analyze it. And then we've got a final method, this direct sniffing of the comet, because the mass spectrometer is actually in a space environment, it's in a vacuum, and by virtue of being in that environment, any molecules that are floating around, some will actually get into the instrument by themselves. So anything that does, we can analyze them as well. So there's, again, lots of belts and braces, because in space missions, things can and often do go wrong. So we needed to try and catch all. So the Philae lander, you're probably all familiar with this now. It's run all over the news, but it's quite a feat. I mean, there's 10 instruments on there. There's lots of UK involvement, lots of European and US involvement on it, and it's the actual lander itself, it's about 100 kilograms of mass, and it's the size of a washing machine. So it's quite a small instrument, really, but it's absolutely jam-packed with science and instrumentation. Okay, so this... in space science, there's a lot of politics goes on. That's Ptolemy, and that's the lander frame. We were told back in 2000 that in Germany, the lander's there, the landing gear's on, all the avionics are on, the control systems are on, and Ptolemy, you're the first instrument on, you're late, because we had a problem. We vibrated the instrument and something broke, so we had to take it apart to fix it, and that put about a 2.5 month delay on delivery. So they're telling us that if you don't deliver your instrument, we will fly a lead block, because all the centre of gravity is worked out for the lander, and if an instrument's late, they can't wait, because the rocket waits for no one, especially when you're trying to get a comet at 3 AU away. So we burnt the midnight oil at the OU and absolutely busted a gut to get this thing finished. And me being the lowest, I was the PhD student at the time, I was there working in the clean room, all hours God sent, 18-hour shifts for 3 weeks. But I had the pleasure of taking it out to actually put the instrument onto the lander. So I donned my clean room garb when we got to Germany, walked in to be met by that. And there's no avionics on it, there's no landing gear on it, there's no control systems. So essentially, there was a bit of this blaming and brinkmanship going on. So what they did is I bolted it onto the lander, and then I took it off the lander and put it in the clean room for 3 months while the rest of the lander caught up. But we had the moral high ground after that, and they did invite me back to actually bolt it back on when it was needed. So the Rosetta spacecraft, ESA don't like flying radioactive generators at all. So the whole mission had to run on solar power. So the actual spacecraft itself, it had the orbit had I think it was 64 square meters of solar panels, and obviously these have to be crunched up for launch and they unfurl. And because of the inverse square rule, sort of when Rosetta's sort of near the sun at 1 AU, there's I can never remember it. Nearly 9,000 watts of power it generates. But obviously, when we're out at the Comet at 3 AU, when we first pick it up, there's less than 1,000 watts. So this was the reason why the spacecraft had to be put into hibernation, because there just wasn't enough power to heat all the systems, run all the electronics and everything. So ESA came with this really amazing plan of putting a spacecraft into hibernation. It's been done before, but never for this period of time. So it was put in hibernation and it was gone. I'll just skip through this one. So, as we know, space is big, so there's an understatement, yeah. So it takes 10 years to get there. So we did. It's actually running. So we did an Earth flyby, and we got some fantastic images of the Earth. Actually, there's something actually worth saying. Actually, we also did a couple of Mars flybys, and again we got some stunning images here. But then we came back, and I think it was on the second Earth flyby, NASA detected an asteroid on collision course with the Earth. So all the alarm bells went out that this asteroid was actually going to collide with the Earth. And it turned out when a European rang them and said, actually, that's one of our spacecraft. So there was a little bit of embarrassment, and then they acknowledged it. So, but I think for 3 days, Rosetta was labelled as an Earth-crossing asteroid. So obviously, as the animation goes on, so on its way out, there was a couple of targets of opportunity. We had a couple of asteroids that we flew by, which were really exciting because it enabled us to actually test out some of the subsystems, the cameras, and the pointing systems before we actually got to the comets. So one of these targets was an asteroid called Leticia. I mean, and it's a stunning object. I mean, it's 130 by 100 by nearly 80 kilometers. So we made a close approach to this object, and the next one shows these sort of images obtained. So we knew the pointing systems were working. We knew the camera systems were working, and also Ptolemy. We actually turned it on as well to try, because Leticia is just about at the size where it may have an exosphere. But it's very, very tenuous. So and it's right on the detection limit of our instrument. So we thought, hey, let's give it a go. And we did. And we detected something, but it was significant. We're not sure it was significant, but we were able to get a paper out of it. So happy days. So okay, so Rosetta is now in hibernation, and we're going to this comet, but we know absolutely nothing about this comet, really. We know its period, and we've got a rough estimate of its size. And this was a slide that was originally generated in 2003, but it was recycled in 2013. Because, just to prove, I mean, these images were obtained. Not images, sorry. This model was generated from light curves generated from the Hubble Space Telescope. So it gives us a rough idea of what the size of the comet is, but we really have no idea. So January last year, the world watched, we watched, everybody was waiting hoping that Rosetta would wake up. Because, again, the engineers were very confident, the scientists, especially those of us that worked on Beagle 2, were a little bit more pessimistic. But we got the signal, and it's just quite interesting. Live on television, we see some of our very reserved German and French colleagues jumping around, hugging and cheering. So so we're really excited now because we're on. So what they did back in February, they pointed the cameras at the comet, and as you can see, again, we're still not really learning much more about this comet. It's just a speck, and I think that image, I think it's 2 pixels, and I think they do some jiggery pokery about it. So we know the comet's there, and we know we're going in the right direction. So a couple of months later, they point the Zeus camera at it again, and you can just see now it's taking on a form. And you can just see a little bit of the coma coming off it. Because, surprisingly, back then there was a bit of an outburst. Sorry, not an outburst as in, but a cometary outburst. And we got a little bit worried because it looked a lot more active than what we thought it was going to be. So there was a little bit of a panic went on. But we think it was just a single event that went on. And we can just see a little bit of the gas on the coma there. So, bearing in mind, this is all happening very, very fast. I mean, we're April, May time. The plan is this lander has to go down in November, regardless. And if it doesn't go down in November, what ESA will do is they will point the spacecraft away from the comet, and they'll eject the lander away. Because what they don't want is they don't want the lander being satellised around the comet and being a collision hazard. So it either goes down or it goes away. So what ESA then started doing through the summer is we started having a landing site selection meeting. It was great European brothers and sisters in Europe all coming together 3 or 4 times in Toulouse and Rome, and nice jollies actually. And what we were trying to do is we were trying to work out where to put the lander. And as you can imagine, you've got a diverse team of some quite powerful scientists who've worked all their career for this, and their instrument is their baby, and their instrument is the most important instrument, and everybody else can go to hell. And I will tell you, all right, no, that's not the way ESA wanted it. So they wanted a consensus. So the plan was over 2 months to try and come up with a plan of where to land. But we didn't know what the comet looked like. We were working on this European comet model, which was like a potato shape, which had no resemblance to what we actually found. So it was a bit academic, really, but it got the teams working together, and it got us trying to work in parallel. But the important things, really, was the scientists wanted to go to the really exciting places, the cracks, the crevices, anywhere where there's gas coming out or outbursts. The engineers, no, we want to go somewhere flat, somewhere smooth, where there's sunlight and there's no boulders. And I'm like, that's not where we want to go. So there was this toing and froing, and the scientists, no, and eventually the scientists came down on a consensus of what kind of place they would like to go to. We still had no idea what to expect, but the engineers were still saying, we will have the final word. So, and what they threatened us, at the end of the day, is if they didn't like where we wanted to go, they would overrule us and put us down on the smooth, flat, boring place. So obviously, as we got closer, we found that. And it's like, oh dear, all this work we've been doing, and you see one going around now, all this work we've been doing, it doesn't add up to what? And it's just like, and you can imagine, sort of like, we're going to land on that? Okay, okay. And it really was a moment. It wasn't good. So, and obviously as we got closer, I mean, we uncovered this stunning object. I mean, it's just stunning. I mean, I was very lucky because in these landing site selection meetings, we were getting these images way before they were being released to the public, and they were coming in, and it was like jaw on floor moment. So when we actually mapped the comets, again, it came very similar to what the Hubble light curve data was giving us. So it goes to prove they were about right on the sizes. But obviously, they didn't predict the shape. And again, this is just I just love this image. It's one of my favourite images. And it was, I mean, we've all got children and we all take selfies, but I mean, that's a selfie, isn't it? I mean, that is a selfie. And at the time, I didn't realise, because obviously I had this image, but I played with the contrast, and I don't know if you can see, I can see on my laptop, I don't know if you can see on the top, but you can see this jet escaping from the neck region, and it's like, I mean, even back then, it was an amazing active object, and so we started again. We had the landing site selection again. So now we're looking at this object, and it's like, oh my gosh, it was head scratching. Originally we were going to plan with 10 landing sites. We couldn't pick 10 good landing sites. We barely picked 5 that we could discuss. So we started off with these 5 landing sites, and they all had things for them and against them. The engineers really liked B, because B was a nice big flat bowl with no boulders in there, and no crevices, and lots of sunlight. But as we got closer and closer and closer, every site looked equally bad. I mean, I've said it before, this was a really unlander-friendly comet. It's just everywhere you look, there's crevasses, there's boulders, and it was back then which we were starting to realise that this might not work. And ESA then started sort of reining in the expectations with the PR, because it just wasn't looking good. So in the end, we picked one of the least bad sites from a bad bunch of bad sites, this landing site J. So basically, on the left, there's an artist's impression of the lander on the comet ready to do its science. And to get there, we had to overcome a few problems. Obviously, the gravity is very, very feeble. The lander itself is 100 kilograms. On the surface, it's the equivalent of probably holding a piece of paper on your palm. So there's a problem there. So to overcome this, the Germans developed these 3 systems. One was the harpoon system, which the idea was to fire the harpoon, 2 harpoons into the comet, and anchor yourself down. And these are very clever because they could handle materials from concrete to candy floss. They're very elegant design. The other solution was these ice screws. So each of the legs had an ice screw down. So when the lander touched down, the energy and the momentum was imparted to screw these screws into the surface to try and anchor it down. And then finally, on the bottom image here was a active descent system, and this was it was compressed nitrogen. So the idea is when it touched the comet, it would fire a jet of nitrogen to try and pin it down to hold it, and that should have fired for about 4 seconds, just to hold it down, to give the other systems a chance to go. And there's a real quick simulation here. This is a simulation. So basically, the lander was going to dive bomb the comet. It had to jink, because if the orbiter didn't take that movement, it would crash into the comet. And then over 7 hours, the lander would fall and hopefully hit its target. So on the day of the landing, we're all in DLR. These are images of myself at the top. It was November, so I was growing my Movember tash, and my mum went mad because I was on TV quite a lot, and she was saying, "Shave it off, you look an idiot." But I said, "No, for charity, it's staying on." But anyway, so we're all waiting, and there's a nervous expectation of it. We'd planned what the instrument was going to do, and at the time people kept saying, you must be really busy, you must be really busy. And we were saying, well, it's really busy trying to make ourselves look busy, really, because a lot of this stuff was coded, and we used like a scripting language, so the instrument was all planned 6 months, well, the last 10 years we've been working on what we wanted to do for the first 3 days and in the extended science mission. And all that was coded, and it's all uploaded to the lander. And it's been uploaded for months. So we just sat around like, yeah, we're really busy. It's really hard work being a space scientist. It's really, but no, we were doing nothing really. We were waiting, and really, we kind of thought we were going to be in Germany as a bit of a jolly, but there just to interpret the data as it came back, and also if things didn't go quite to plan, and there's opportunities, like if an instrument fails and they say, can your instrument run in its space? So it was more just as a bit of a reactionary. So we planned out what we wanted to do for these 3 days, and we were all good to go. So I don't know, so you can probably remember back to the day, and this is the thing that sits in people's minds. Do we have sound? Is there any sound? Or? Sorry, it's really... Doesn't matter. Anyway, you can probably remember this. This is my head of department, and what it was is all the people doing the work were in Cologne. All the dignitaries, the politicians, the press, the stars, and the TV were in Darmstadt. And what Darmstadt is the German headquarters of ESA. So we're in our little room watching this live on television. They're all clapping themselves, drinking champagne, and we're thinking, no. And it was really embarrassing. It was like a car crash playing out live on television. We're trying to text them, ring them, say, stop, it's not good. This is not working. This is not going as you planned. And they're all, well done, champagne's out, and all the harpoons are fired, we're down. And we're getting this live data stream coming back in. And that's enough of that. Sorry. So we're getting this live data stream, and you can see by the faces. I mean, obviously it's like, gosh, this is not going to plan. We were texting and calling our colleagues at Darmstadt, and obviously the phones were off because they were enjoying themselves too much. But the image on the far left, this is the telemetry that's coming up from the solar panels. So what we should have expected, if we were down, we should be having those, because the whole lander is covered in solar panels. So we should be having telemetry, steady line. This is what we were getting. So we knew the spacecraft was, the lander was tumbling. It was tumbling, rotating. We were getting link breaks. So it was like it was going pear-shaped. This was coming through. While all this was happening, while all this was happening, our instrument was the first, after touchdown, 9 minutes after touchdown, the data, our instrument should have turned on, done an analysis, sent the data back. So all this is happening, we're all thinking, ugh, Beagle 2 again. And then we got packets of data coming in. And we're like, wait, we got data, and if you see the guy at the back, I don't know if you can see him holding his head. He's another colleague, he's a German colleague who had an instrument, a mass spec as well. And our data was coming through, and he didn't seem to get anything, so he's looking quite full on and disappointed. So we're bouncing around getting really excited now, like Monica was. Yeah, we've got data. And then more data starts coming through. So every instrument starts getting data back. And then we had a bit of a crisis meeting, because obviously we didn't know where we were. Then we knew the spacecraft was still rotating, but it was still doing what it was supposed to be doing. It's like, are we on the comet? Have we left the comet? Are we leaving the comet? So this, obviously, it transpires, we now know what happened. And this is another stunning image. It's like, this is the image from the orbiter, actually looking at the comet as Philae goes bouncing across its surface. So, I mean, it's just phenomenal. I mean, it's tiny. I mean, it's pixels, and they've time-stamped it, and we can plot the track. And I'm not sure if you can see it on the touchdown point before, but you can actually see the indentations that the landing gear made as it scuffed the surface. So, I mean, all these images are lifted from the ESA website. So, if anybody's interested, there's a wealth of information on the ESA website.
So you had bounds on the comet?
Yeah. We hit first, bounced, then came down again, and then we think another time, but we're not sure. But we think the lander may have then rotated, and then smacked into where I think.
Is this an Olympic event?
Well, interestingly, is for us, scientifically, it's amazing, because what we actually managed to do, we got data sort of in the first bounce, 9 minutes after touchdown, and we sampled that whole cloud of organic material we shoved up. So we got all that data, which we got a science paper from. Yes. Thank you. Yes, yes. And then, when we came to a stop at this place, this different place, because obviously we decided, and Lisa decided, we were not able to run the plan, what we planned. So it was just while we were there, because everything changed. So we ran our instrument 6 more times, and we got a completely different signature there than what we got at the first touchdown. So we know the comet's different in different places, which is a really big thing. And we got another paper last week on that one as well. So we've done all right out of it. But so anyway, so we came to a stop here. And obviously, when these images came out, again, it was like, oh, yes. And interestingly, it doesn't show it here very well, but it's, the more you look at it, you're seeing more finer and finer detail at higher resolution you look, and there's just so much structure in it, and it's just an awesome place. And it's not at all what we actually expected at all. We expected quite a dull, boring thing, but it's certainly not a dull, boring place. And this is the PI in one of the meetings. This was his sketch of how he thinks the lander came to rest. So what you're looking at there is you're looking at the top of the lander facing out, with the bottom of the lander facing into a cliff. You can just see his little pictures of the sun going over the top. So, yeah, so I say, so we modified our sequence on the fly, and this was normally when we write sequences and send them up, we spend months doing it. We check everything, we run it through. We've got a spacecraft simulator. We then send. Well, in fact, you can, on the middle image there, one of my colleagues, there's those 2 boxes. There's actually a spacecraft simulator, so we generate our code, pass it through the spacecraft simulator. If it doesn't fall over or hang up, we then send it to Cologne, where they've got a model copy of the lander with all the other instruments on. We then run it there to make sure it doesn't interfere with any other instruments, and then only then are we allowed to send it up to the spacecraft. Obviously, we had 60 hours, all that went out the window. We wrote our code, rammed it straight through the spacecraft simulator, yeah, good, go, and that was it. Yeah, no, exactly. And this was our final experiment, because the 2 images at the top are the voltages and on the battery, and we knew the battery was starting to deplete, and there's a magic voltage of 19 volts. If it gets below 19 volts, the lander shuts down, and that's it, game over. So we knew Ptolemy was quite power hungry, so what we wanted to do, we wanted to analyze our case oven, because we thought that some of this material that's been messed up would have landed on it, so we could have had a grab at some solid material. So it was a bit of an all or nothing, to be honest. Oops. So on mine, I put some nice little lines, but they've not come up on here. But essentially, you can see that's the volt. The top one is the voltage decaying over time, and it's dropping. And then you see the big dip. That's when we turned on, and then the change in grade is. Sorry. So we turned on there, drop, and then we turned Ptolemy off there, and then it came back up and carried on decaying. And it turned out we probably had about 30 more minutes of power in the battery, but it was a little bit close to the wire for us. So again, it was widely reported. It was a complete success, and we had our data. So I'll quickly rattle through this quickly. So the active descent system, as you know, the cold gas thrusters didn't work. The harpoons didn't work, and the ice screws didn't work. The only thing that saved us was this passive damping mechanism, which was to look at it, it was a bit Heath Robinson. It's the sort of thing you'd make in your garage. There was like springs, pulleys, and string, and it literally was pretty low tech. But the idea there was to damp out half of the energy on collision, and that's essentially what happened. And that's why we actually stayed on the comet. We didn't bounce straight off. By virtue of, as I was just saying, Jonathan, by virtue of bouncing, we've actually sampled 2 different sites. which in the plan we weren't able to do. So we're really happy because we've sampled the Agilca and the Abydos sites, and we've learned a lot of information. And these images haven't come out very well, but these are just the raw data that went into our recent papers. So I don't know if you can see on the top graph, there's a number of peaks, sort of. They're all organic material. So and then the one at the bottom is at the Abydos site, which we're not seeing the organics, and we're seeing CO and water. Okay, so science objectives. Overall, it's been quoted that the lander was 80% successful. Obviously, some science was lost. Ptolemy, we got probably 40% of our primary science done, but we also got some bonus science done by virtue of being at this second landing site. So quickly, the status at the moment. Went into hibernation, and in June, we re-established contact again. And in that first contact, it was a 78-second contact. We got 343 packets of data. And then over the coming weeks, there was a subsequent number of communications. And in those windows, we got quite a lot of data back out the lander. And what that data showed us that, because basically a lot of that is historical data as well as also as data from now. So it was determined that the lander had been coming on since October. Since April, sorry. So it had been coming on, doing its thing, going to sleep again, coming along. But the problem was the spacecraft, the orbiter was so far away, because the actual RF link was really only designed for about 160 kilometers. So we were about 200, 180 kilometers. But the reason the spacecraft was so far away is as the comet comes in close approach to the sun, it becomes very active. So there's a lot of material coming off, gas coming off, and ice coming off. And there's an automatic system on the spacecraft called a star tracker. So, and this uses, it basically picks 9 stars, locks onto them, so that the spacecraft knows where it is. What was happening, when the orbiter was getting close in, it was picking on bits of ice. And it was like, yep, you're a star, you're a star, you're a star. Oh, where am I? And then it goes into a safe mode. And they nearly lost the spacecraft. So they backed it right off to a safe distance. What's happening now, though, is the comet's gone around the sun and it's on its way out the solar system again. So it'll start to calm down, cool down. And the plan is to actually come in close again. Because all of these communications, when we first landed, the orbiter was about 16 kilometers away from the surface. So the plan is to come back in close again and try and re-establish communication with the lander. Because the engineers, again, are really hopeful that it's probably survived. So hopefully, so what next? Okay, still in orbit. The mission's been extended to September 2016. And the plan then is, at the end of the mission, they're going to actually land the orbiter onto the spacecraft. So Europe will have successfully landed 2 spacecraft on a comet. So controlled landings. So, okay, thank you very much. Any questions? Actually, one more thing. Sorry, I don't know if anybody has children or involved in education. One of the other things we do quite a lot of outreach from the OU. So if anybody wants visits to schools, we've got quite a good outreach. We've got meteorites and space hardware, and we're happy to come in. So I don't know. I'll scribble my email down if anybody wants to get in touch. Sorry, go on. Yeah.
Yeah, got time for questions. Got time for a couple of questions.
Thank you for the talk.
No problem.
If you could do the mission again and you didn't have the limitation from ESA about nuclear power, would you have used nuclear power?
Oh, yeah. And I'd have 2 landers as well. I'm greedy. Or probably 3. I mean, one of the things we've been working on also is penetrator missions. And it always makes me snigger a little bit when I say it. But what they are is they're essentially artillery shells, which are instrumented, and they've got a deorbit engine on them. So you can fly around your place you're interested in, a comet or an asteroid or a moon, and you can say, I want to go there. And then you literally press the button, and you launch your penetrator. And they deploy 15, 20 kilos to where you want to go. So one of the things we're looking at is trying to use that technology as opposed to soft landers, because soft landers are great, but as we know, they don't always go right. And one of the issues is to actually get access to that material that you're interested in is often subsurface. So if you can hit the surface at 300 meters per second, go a couple of meters below, you're down where you want to be. So yes, I would. So I'd say, yeah, I'll go nuclear, and I'll probably have a lander, possibly 2 and some penetrators as well. So greedy.
Thank you very much. That was fascinating. So as far as the orbiter needing to land,
Yeah.
since the lander landed as it did,
Yeah.
have the plans for how the orbiter is going to land changed at all?
No, I mean, the thing is, we still haven't even found the lander yet. There's been a lot of looking. There's a couple of sites where they think it might be. And what they've actually done is they've passed the images over to the military people to use their fancy image recognition stuff. But there's what they're finding is, everywhere they're looking, they're finding landers because it's right on the limit of it's like 3 pixels. Oh, it could be there. There's one there. There's one there. There's one there. But no. So we haven't found the lander. But to answer your question, they're actually putting the orbiter down. It's a last ditch thing, really. Because the second it goes down, we'll lose communication to Earth. So the idea is to bring it in really slowly and get some stunning images and try and do some more science and give all the other instruments a really, really close-up chance. But it is a complete, game over mission. So, yeah.
Hi. Hi, great talk.
Thanks.
What's it like coding in an environment where your devices may be affected by cosmic rays? You may lose half your memory or something?
Yeah, that's certainly one of the things we have to look at. And it's, I think it's been said hundreds of times, but in the space missions, we're really conservative. I mean, we're flying, the processor was a 286 equivalent back in 2000. So it's many generations behind the state of the art. So and what they do is everything has to be radiation shielded or radiation tolerant. But certainly with Ptolemy and with the lander, they have backups and they refresh. They have dual redundancy and sometimes triple redundancy. And they do. I mean, it's above my knowledge, but they do clever polling to make sure that everybody agrees, voting to make sure everybody agrees. So. But yeah, it's something we have to be very, very mindful of.
Hi, a similar question actually. I was just wondering if you could talk a bit about how the data gets transmitted and whether it just sends packets one at a time and fire and forget, or if there's any guaranteed delivery, and also just for the strange question of if an alien found the lander, is it got an outbox? Do they look back and go, oh look, it sent all these messages, or is it just burn them when it's done? I don't know.
No, it's I'll try and answer the first one first. I don't know. No, we have checksums, and there is a two-way thing. So basically, the lander tries to send it, and then the orbiter then says, "Are you sure?" And then yes, and then there's checksums back from the orbiter back to Earth. But I'm not totally familiar what the protocol is. Sorry, and there is there's a mass memory store on the lander which archives all the data. And what happens is it's like a FIFO, so stuff comes in, it's in there until it's chunked out the top end. So after it dies, they'll be able to see the last few things that we've asked it to do. Which actually, one thing I didn't mention is just before the very last contact, what we did. Sorry, after the last contact, what we did is we bombarded the comet with instructions for the lander to do more science. So the plan was we knew we were having to back off, and we were hopeful that we can come back in and make communication links again. So because we knew the lander was working really well, the battery was fully charged, and it had done exactly as designed, we've instructed it to do a lot more science. So hopefully that outbox is full of of science. So if we don't get it, somebody may get it. Yeah. It's really annoying because there's more papers in it, so I want it. So.
All right, I think we're close on time. Thank you very much.
Thank you very much.